This is a fairly standard statics problem as well here. What you have in this case here is you have a wall here, very strong wall that isn't going to move, and you have a beam coming off the wall here. You have a cable here holding the whole thing together, and you have someone walking on the beam. So a very common question, or in this problem like this, something that might be related. So what would the tension in that cable be to support the whole thing? And just a couple things we know here. You'll have to fish them out of your own problem. We'll call the beam's mass a capital M. We'll call the person's mass a little m, and we'll call the length of the beam L. And I think we can sort of work out some of the statics logic and so on, just keeping it general like this with those parameters in mind. So let's see what we have. One thing to stay at rest. Statics demands that the sum of the x force is equal to 0, the sum of the y force is equal to 0, and the sum of the torque is equal to 0. Those are the demands of statics, and we want this thing to stay put. Okay? So what we should do first then is go ahead and identify all the forces acting on the beam. We want the beam to stay fixed. The beam is going to be our focus right here. So don't worry about the person or the wall or anything. Focus on the beam. So what we have in the beam, of course, is we also have the beam's weight acting straight down. We can call that capital Mg. And if the person is sort of out here at a distance x, say, from the wall, we can call that distance x here. Then we'll have the person's weight down as well. We'll call that little mg. Those are two forces acting on the beam already. The tension is a force that pulls away from this point of contact, so it will definitely be a tension in the rope like that. And believe it or not, there's two more forces which are kind of strange that, say, haven't come up with anything we've done, at least in this course, this quarter here, is that the hinge is definitely maybe pushing on the wall, pushing on the beam this way with an hx, and it's probably also pulling or pushing up that way with an hy. So yes, there's a hinge force acting on it. Something has to support the beam over on this side, and we'll just call it H for hinge because we know there's something there, or N for nail, or G for glue, or something like that, but there has to be some force to support that end of the beam right there. Okay, so with that, I think we have all our forces in mind. Let's go ahead and start filling these equations right here. So if I look at the sum of the x forces on this system right here, what I'll get then is I have the hinge force over to the right, and then I have a minus t times the cosine theta over to the left. All that's equal to 0. So look very carefully what I've done here. The tension is a vector right here, and vectors usually have two components, at least when they're in two-dimensional space like this. There's definitely going to be a tx that way and a ty up like that. So there are two components of tension sitting in there. Okay? So what I've done is I just recognized that. The hinge is in the x direction, and t cosine theta is the x component of the tension. All those are equal to 0. So you have your first result here. The x force that the hinge has to support is equal to t times the cosine theta. So there's your first result. I think hopefully it's a bit intuitive to you then that the amount of rightward force the hinge has to sustain is sort of equal to the x component that's in the tension. Like if you keep cranking on this wire here to make it tighter and tighter and tighter, the hinge has to sort of push this way stronger and stronger and stronger to sort of support that tightening that you're doing. Okay? Continuing, the sum of the y forces, those have to be 0 too. Let's see what we get for that. Well, what y forces do I have? I have a hinge, y component of hinge up. I have the weight of the beam down. I have the weight of the person down there and there. Then I also have the y component of the tension right there, this t sub y, but that's up. So I'll have a plus t times the sine of theta, and that's going to be up. And all that's going to be equal to 0. So you have another sort of preliminary result here. Now the y component of the hinge force here, if that's your focus here, is definitely equal to m plus little m times g. So on the one hand, the y component of the hinge has to support the entire weight of the beam and everything that's on it, but it's relieved just a tad bit here by the upwards pull of the tension, the minus t sine theta in there. That just comes algebraically. So there you go. There's another result for you right there. Okay? So we don't really have any results yet, but we just have a little intuition about where the forces on a hinge come from. They come from, in this case here, just the horizontal tension. In this case here, the full vertical weight and a bit of vertical tension in there. Lastly then, we want to see that the sum of the torques is equal to 0 because we don't want the system to rotate. You can imagine a disaster like this when someone's on a system like this that sits like this and it starts to fall like that, or the tension gets too large, it starts to go up like that. We'd really like it to stay at rest rotationally, and that's what the sum of the torques equal to 0 will ensure us. Okay? To make things easier once again, we have to find a pivot point for ourselves, and so we'll place the pivot point right here. The hinge forces are kind of strange and definitely unknown, so why not place the pivot point right there so they will knock themselves out of the torque equation. So if that's the axis of rotation, we're measuring everything relative to this axis right here. So the hy and hx both have 0 moment arms, so they won't be in any torque equation. So we'll just go ahead and leave them out. But we'll continue then and try to get everything else in there. Okay, and the torque sign convention will follow as is typical. You can choose anything you want. I'll just choose this one. Anything that rotates clockwise can be positive. Counterclockwise negative, we'll just go at it that way. Okay, so the first force that I recognize is the weight right there, which acts at distance L over 2 from the beam right there. So plus L over 2 times mg, and here's the axis of rotation, here's the moment arm, and there's a 90-degree angle there, times the sine of 90, and we're good. So the normal, well, I'll go ahead and put it in just for the sake of instruction right here. Here's the sine of 90, which will eventually be 1. Okay? Continuing on, I see the weight of the person right there, and the person's acting at a distance x from the axis of rotation right here. So there's the person's x times the person's weight times the sine of 90 degrees. Okay? There's another 90-degree angle between the moment arm right here and the force of the person. And the last force I see in the problem is the tension over there, which acts all the way at the length of the beam's moment arm from the axis of rotation. Here's the axis of rotation. The moment arm is all the way down there. L times T times the sine of theta. So that's the torque due to the tension right there. I don't see anything else acting on the beam, so I'll set all that stuff equal to 0. Now what you're left with sort of is, more or less a big mess, but you can simplify it a little bit here, get rid of the signs at least in there. So we have an L over 2 times an mg plus an x times mg minus LT times the sine of theta. So I'm actually just going to stop the problem here because I'm not sure exactly what your needs might be, but we'll just sort of leave it like this because there really isn't any more physics to possibly do. Now it's your turn to look at the numbers and the questions and exactly what the homework problem or the book problem might be asking for here, but the equations that you have are right and sort of can't be dealt with any different level here. There's the hinge force, there's the hinge Y force here, and here's one that relates to tension. So like, for instance, if you had a homework problem that you knew what x was, you knew how far the person was from the axis of rotation, you could fill in some number for x right here, maybe something like 2 meters. And if you knew how long L was, maybe something like 5 meters. If you knew these things, and you knew the mass of the beam, and you knew the mass of the person, and you knew that G was 9.8, then it would be possible in this case here to solve for tension. You'd actually get some numbers, so you'd be able to figure out exactly what the tension would be. But I'll leave it up to you. But these will definitely be your guiding equations, independent of what your textbook might be asking for this system.